my pleasure to have Brennan here, coming from Colorado School of Mines, right?
Yes. Yep.
And so Brennan is a PhD from ISAM. We all I think it's about a year.
1 year, yeah.
1 year, yeah. And so he finished his PhD with Milish Patanka.
Yep.
And you worked on quite a few things, but I remember that at some point you were doing some fluctuation stuff with membranes. And then he moved and he did a postdoc in Quran with Alex Dowden, doing a lot of, the part that I know it's about suspensions and simulating suspensions and beautiful collaborations with Michelle here on active matter. And then he got a job and he's now assistant professor in the applied math department in Colorado. I assume you like skiing.
I don't. It never made any sense to me. I don't know.
Anyways, I think it's exciting. An alumnus of our department with a very successful career in math, and let's see what he has to tell us today. Welcome, Brennan. Welcome.
Thank you, and thanks all for coming. So just to get into it, I'm going to talk today about a method for measuring diffusion, or actually more generally, dynamics in microscopic suspension. So the word diffusion really refers to the apparently random motion of very small things. So think like micron-sized things. To give you a sense for what a micron is, it's 1/1000th of a millimeter. So I kind of think of it as like, it's the first length scale that I really can't see. If you put a micron-sized thing in front of me, I could not see it. So these are properly small. And I will talk a fair amount about what diffusion is, and some of its more interesting and exotic properties, but that's sort of the long and short of it. And to put a picture in your head, here's a video. Here's a video of colloidal particles diffusing. So this will be kind of the model system we'll talk about most of the time. The video is a little bit laggy, but you know, that's what this will be. The idea is that colloidal systems are simple systems that can tell us a lot about complicated systems if we can understand them well. The colloids here are these small spherical particles. They're in a fluid, they're sedimented above a microscope slide, and here they're just wiggling around randomly. So let's talk a little bit more about random wiggles. Before I do that, a bit of an overview. So we want to understand that randomness. We want to understand the random wiggling of these microscopic particles. And we think we have a method to do it in a pretty robust and kind of mathematically interesting way that we call the Countoscope. And this is just the high-level overview. You take that video that you just saw, these colloidal particles sort of jiggling around, and you draw a box. You draw a box around some of them, and then you count how many particles are in the box. And over time, particles will fluctuate in and out of this box that you drew. You drew it, so it's arbitrary. And you can keep track of the number of particles in that box, and you get a number trajectory. And from that number trajectory, maybe you can back out some statistics that tell you something about the physics of the system. This is the basically top-down, high-level picture of everything that I'll talk about today. So to give you an outline of the talk, I'm going to start with history. And maybe some of you have heard this history before, but I think it's germane to the conversation here because it actually informs a lot of this method and a lot of why the state of the art for measuring diffusion or measuring dynamics in microscopic systems might actually be a little bit lacking. And there's kind of a cool historical anecdote about a very good idea that we were inspired by along the way. So after that, I'll spend a lot of time talking about this counting strategy that we call the Countoscope, how you can use it to measure diffusion and how you can use it to measure even more exotic properties about diffusion. I'll mention a little bit about numerical simulations, and rather than focusing on how we actually did the simulations, I'm going to try and focus on what we can learn from simulations because they're a beautiful tool. They let us turn physics on or off, which is a really wonderful way of looking at the world. And then I'll end by like, okay, so we have this thing, what can we do with it? And some extensions that we're looking at now and kind of new ideas that we're excited about, particularly in out of equilibrium systems. So I also want to talk about, this project came out of kind of like a short idea. I was talking to Sophie, I was in New York, I was talking to Sophie Marbach, shown here in a lab, just about counting and how counting is kind of an interesting thing. When you're counting particles, really it tells you something. And it kind of ballooned and snowballed into this really cool project that now takes up like a lot of our research careers. And it's funny that, you know, things that can be very exciting have little starts. So this is Sophie Marbach, who is at Sorbonne, and this is Alice Thorney work. I like these pictures because Sophie here in the lab actually was the lead on all the theory in this project, and Alice was the lead on all the experiments. But it was a lot of fun. Still is a lot of fun. We're still working on a lot of stuff. If you are someone who likes to read a paper during a talk, here's an archive, or here's a QR link to the paper. No judgment. I do this all the time. So I'll leave that up for a moment. This is the first paper on all this stuff. I'll talk about a couple of papers. Okay. So I'm going to start off with history. So a very, very long time ago, in 1827, the first time anyone really noticed the notion of diffusion, it was Robert Brown, who was a botanist. He was looking at pollen grains under a microscope. It was dogwood pollen. I have no idea why I remember that it was dogwood pollen, but it was dogwood pollen. And he noticed that the pollen was just sort of jiggling around, much like this video, which will probably be a little bit shocking. So this is approximately what Robert Brown noticed. This is 1827, so you probably thought it was ghosts or something. Like there was no physics, there was nothing to say why this would be happening, but he was a very good and very fastidious scientist. So what he wanted to make sure of was that it wasn't biological, because now we know a lot about, say, bacteria, which have these flagellar motors and they're moving around. They're living systems that are moving because they're alive. Maybe pollen's alive. So what he tried was he put it in a lot of different liquids that would kill any kind of life and noticed that it was still randomly jiggling around. So while he proposed no mechanism for this, he did verify that this was not biological. This was a fundamental physical phenomenon. I have to be out of presentation mode for this one. So it wasn't until 1905 that Albert Einstein was the first person who thought what this might be. And the idea was, what if this random motion, this purely random motion, was due to collisions with solvent molecules or atoms? Of course, they're molecules, but I'm using the word atom here to mean the atomistic theory of matter, which I was shocked. I admit my lack of historical knowledge. At the outset of this project, I was shocked to find out that this 1905 paper from Einstein, where he really proposed that diffusion was coming from molecular collisions, is widely considered to be the first real evidence for the atomistic theory of matter, which is wild. So this was an important paper. By the way, it's worth noting this is a cartoon. These blue balls are water molecules, the real thing. I actually rendered the real thing. It looks ridiculous. There's, I think, 10 to the 9 water molecules in like a micrometer of water. So this is a cartoon. This is not what it looks like. Okay. So what did Einstein do? Einstein didn't want to just have this idea. He wanted to write down something testable, actually use mathematics to come up with, okay, if this is the apparently random motion of things from collisions with solvent molecules, how can we actually back out what that was? And the central quantity he thought to look at was called the mean square displacement. So if all you're seeing is some dot moving around kind of randomly, this is the same video as before, I'm just not rendering the little blue dot. If all you're seeing is some particle moving around randomly, you can trace its trajectory out and look at the average of the squared displacement of the particle's position. And he said, all right, you know, I bet this is linear. I bet this is linear in time. And there's some constant of proportionality to that linear. It, of course, depends on the dimension. But the interesting part is there's this constant of proportionality d, which he calls the diffusion coefficient. So not just that, but you can actually write down what the diffusion coefficient ought to be. So thermal fluctuations, it looks like maybe they're batting this thing around and maybe they're injecting energy into the system, but that can't be. So where's the energy going? So it must be balanced out by dissipation. So this is this famous idea of fluctuation dissipation balance. This thermal energy unit, which you can say is maybe proportional to the temperature in the system, the constant of proportionality is Kb. must be somehow balanced out by the friction or the drag. And I apologize for not knowing this date, but sometime in an epsilon neighborhood, Stokes had written down an equation for the drag on a spherical particle with radius A. So you can argue that this diffusion coefficient is related to kBt, which is our unit of thermal energy, and the drag on a spherical particle. So just to give you an idea of what this thing is, if you plug in numbers for this, so a micron-sized particle at room temperature will take about a second to diffuse its diameter. A me-sized particle will take about 10 to the 12 years to diffuse my diameter. So small things tend to diffuse, and me-sized things tend to not diffuse. I prefer to walk. Now, it's worth noting that I was able to do these calculations because I could go on google.com and look up some of these numbers, like kBt, or rather, I didn't have to look up the temperature, but Boltzmann's constant. I could look up Boltzmann's constant. This was not always a luxury that people had. In fact, we didn't even know Boltzmann's constant. What Einstein did in this 1905 paper was lay out a roadmap for how to actually measure some of these things and stopped short of measuring them. That wasn't until... That was supposed to be a good click moment. Okay, that wasn't until Jean Perrine in 1913 actually did the measurement. So what Jean Perrine did was he set up a microscope and projected it on a wall. And then traced out the motion of these particles as they moved. Now, this isn't just a cartoon, this is a snapshot from Perrine's actual paper. So these are trajectories that Perrine traced out from these projected experiments on a wall. And then once you have trajectories, Einstein's paper tells you to take the mean squared displacement, look at the slope, and then that'll tell you something, not just about kBt, but Perrine argued that also it'll tell you something about Avogadro's number. So Perrine actually made the first measurement of Avogadro's number. All these physical constants turn out to be related. And this paper, now called Les Atoms, got him the Nobel Prize in 1925. So this is to really kind of bring home the idea that calculating mean squared displacements, making an actual measurement in a microscopic system tells you something numerically, quantifiably about how it's diffusing. But I regret to inform you that Perrine's work was in 1913, and up to a little bit of computer fanciness, we're still effectively doing the same thing by and large. Particle tracking is, I would say, the most widespread way of measuring diffusion in the modern era. And the algorithms go like this. So you take your video and you break it up into frames, and at some frame, you decide every particle has a color. Really, it would be a numerical label, but for visual purposes, we'll say it has a color. And then you look at, say, the magenta particle here, and then you look at the next frame. Well, in the next frame, there's a particle that's pretty close to where the magenta particle was before, so this one must still be the magenta particle. And you go through, and you can probably imagine how to program this, and then all of a sudden you can take a video and turn it into a trajectory. Once you have a trajectory, you have a diffusion coefficient. Wonderful. You might imagine that if your frame rate is really high, this straight up doesn't work. Particle tracking is pretty fraught. There's all these hyperparameters. How close do particles need to be for you to say that they are the same particle? What about your resolution? What about pixelation? I mean, what if there's drift in your system? What if your microscope's on a little bit of a tilt? There's a lot of problems with particle tracking. And I'm not going to say we solved all of them, but I think the method solves at least some of them. And it's based on this idea from, I was just talking trash about how we're doing essentially the same thing that we were doing in 1913. So let's upgrade a little bit and do essentially the same thing that was done in 1916, which is, slightly later. Marian von Smoluchowski came up with basically this idea of counting. Smoluchowski noticed one of the hardest parts about particle tracking is that back when microscope fields of view were very limited, one of the most annoying things is you're following a particle and you're following a particle and you're following a particle and then it leaves. And what do? So we thought, why not use the fact that there is a finite field of view to our advantage? Let's count the number of particles inside the finite field of view and then see if we can't back out some statistics from that. And he has this wonderful paper, which actually has not been translated from German as far as I'm aware. Where he does this. So notice, I don't know if you remember, I showed some trajectories of particle counts. This is handwriting particle count trajectories. And then above it is actually the numerical sequence. And you can calculate autocorrelations of these things. And he argued somewhat incompletely that you can calculate an autocorrelation and maybe it tells you something about diffusion. So I would wager that a lot of what we did was kind of polish this idea up a lot. This was the core idea of counting. But the two things that we did were A, actually figure out what this thing equals. B, autocorrelation statistically a little bit fraught, so we prefer instead to use mean squared displacements because there's a subtraction and the subtraction can help you out. So get rid of autocorrelation, actually figure out what this thing is in terms of diffusion coefficients, and don't just put up with one box. Subdivide your domain. Get a bunch of different boxes. More boxes, more statistics, more numbers, more matter. Now, I want to take a moment to talk a little bit about why this is an interesting strategy and why it has some potential to be a lot more successful than other traditional methods. By subdividing your domain into boxes, you can really naturally account for heterogeneity. So let's say that you have a temperature gradient in your system. If you just track a particle trajectory, what does the diffusion coefficient even mean? You compute a mean squared displacement or something, and the diffusion is changing as it moves from left to right in the domain. But here we can draw a box, calculate a diffusion coefficient only on one side of the domain, calculate a different diffusion coefficient only on the other side of the domain. It gives you spatial resolution. It gives you the ability to pick out where you want to measure diffusion. We can also use this strategy out of equilibrium. This is something I'll talk about a fair amount at the end, as well as one of the most fraught kinds of systems for particle tracking is dense systems. So there, if your frame rate's not very high, all of a sudden, it's really, really hard to tell from frame to frame which particle is which. It's hard with your eye, it's hard with a computer, it's even hard with modern machine learning to tell which particle is which from frame to frame. Yeah.
I probably should wait because you are going to tell me anyway. But I've been very curious why the boxes have spaces between them.
I love that you asked this.
I've been holding my hands since you first showed it. So kudos to me for being so patient.
I have done this to avoid a potential statistics question, which is, if they're separated, then one can, I would say, fairly easily argue that statistics in each of these boxes are uncorrelated, and we don't have to worry too much about fancy statistical methods. If they're overlapping, they're correlated. If we overlap them, the method works great. There's no problem. More data, even though it's correlated, just goes to more better. But I don't know why. So it does work better when you overlap boxes. And it does introduce a correlation length, and that's great, but I'm a little reticent to say, yes, this works 100% of the time, all the time. So I do the separated boxes so that I can say, this works 100% of the time, all the time, and we don't have to worry about correlations. I think there's a bunch of genuinely interesting statistics problems in this. Like,
I was thinking about if the boundaries overlap, you would have to decide if a particle is one box or another, right? And you would have multiple counting problems potentially. But it's interesting that you do overlap. And
all we do when they're overlapped is you double count. So it's in one box, it's also in the other box.
Yeah. And apparently it doesn't change anything. Which is. Yeah.
And so we can look at it numerically at some point. There's diminishing returns, as you might expect. But so far, Greek don't rise. Oh, works well. So good question. Okay. So these are a couple of systems where we really like this counting approach. Okay. So I want to mention, for the rest of the talk, I will be showing a lot of these pictures of experiments. The data collected for this is completely unreal. Eleanor, who's a graduate student, got like 48-hour data sets of these colloidal suspensions with like no drift. I have no idea how she did it. She's a wizard. And so anytime you see a picture like this, just know that an incredible amount of work went into to get that data. So, there are two kinds of suspensions that I will talk a lot about, at least in the first part here. dilute and dense suspensions. And I just want to talk a little bit about what that means and assign a number to it. We usually think about these things in terms of packing fractions. So the packing fraction is, you imagine all these as disks. They're spheres, of course, but when we're looking top down, they're disks. If you just look at the area of the total disks by the area of the observation volume, that's the packing fraction. That's the in-plane packing fraction. Dilute suspensions have small in-plane packing fractions, and dense suspensions have large in-plane packing fractions. As a side note, something very interesting happens when the packing fraction gets to 0.68, it becomes a crystal. That's the crystallization. So it's just below the crystallization transition, where it's still a liquid. So weird stuff happens. Anyway, I'm going to start by talking about dilute suspensions, though, because we can say a lot about dilute suspensions, and these are still, by all accounts, very interesting in their own right. To show you a video, this is a video that I've showed you a couple of times, but I just want to point out a couple of things about it, which is that, again, a little bit choppy, but if you kind of follow particles around, maybe occasionally they'll make friends with each other, they'll be close, but by and large, they're fairly far away. So in dilute suspensions, we really, it's I would say, a successful theoretical strategy to think about these things as being well separated enough that they're on average not interacting with each other. So we can usually kind of consider this as a bunch of particles basically on their own. Now, I kind of mentioned this before, and here you see the well-separated boxes. Again, this is because I don't want to worry too much about correlations or anything. But the idea is we tile a plane with boxes, we count the number of particles in each one of these observation boxes, get a bunch of trajectories for all of our boxes of some size, and then compute a mean squared displacement. Up here, I just wanted to include a little anecdote that computing mean squared displacements of particle count time series is actually related to autocorrelations. So it's in some ways similar to the Smoluchowski idea. Yeah.
So here the boxes are like the size of the particle. Is that just for like how do you count half a particle?
No, yeah, these are actual size.
So do you count fractional particles?
So this is a good point. We've actually been meaning to screw around with that and haven't yet. What we do is we just say if a particle center is in a box, it's in the box. Okay. If the center is outside of the box, it's outside of the box. I think it would give you cool stuff if you counted fractions of particles, but
you just want centers.
We haven't done it yet. Yeah, so now we're just counting centers. And yeah, and it's even in some ways a successful strategy to think about boxes that are actually less than a diameter of a particle. You can really go wild. The reason this is called the Countoscope is you'll see that you get kind of different notions of dynamics at different scales. You can look at big boxes and get collective ideas, and you can look at small boxes and get self ideas. So what do these mean squared displacements actually look like? So I kind of have a color code over here. The big boxes are in yellow, the small boxes are in orange, and you get these curves that all have kind of a self-similar form. For these small boxes, it's really well resolved because we have a lot of statistics. You see that there's this is a log-log plot, so it's not actually linear. There's this short time power law behavior, and then it kind of saturates to a plateau. I'll talk about the plateau, but I want to focus on the short time power law behavior. You notice that the power law behavior is t to the 1/2. That's already, in my opinion, kind of neat. Mean squared displacements of particle positions give you something linear scaling, which is a signature Brownian motion. The fact that the scale is like t to the 1/2 is, in fact, a signature of fractional Brownian motion. So while particle counts themselves are regular, by the book, Brownian motion, all of a sudden when you count them, you get this more exotic fractional Brownian motion. This actually counting regular, pure diffusing particles in a box and then getting a time series for that is the simplest example I know of for fractional Brownian motion. But it's a somewhat exotic property. So not only that, we can actually quantify at short times what this mean squared displacement ought to be. And I think apart from the 8/√pi, which is a little bit weird and comes out of the math, but I think it's almost kind of natural. It depends on this teal quantity here, which is sort of the mean number of particles in the box. How many particles you would see on average if you imagine this thing is ergodic and you take statistics. It also depends on the square root of time. That's that fractional Brownian motion thing. And then it's divided by L squared. L is the length of the box. divided by d. So L squared over d gives you a natural time scale. This is a time scale associated with diffusion in a box of length L. So that pops out just totally naturally. And you might hope that, okay, this is a really nice characterization and all these plots are pretty self-similar. So hopefully if I rescale everything, they're on top of each other. And indeed, this is the case. So because all of these plots, all these different boxes in this dilute suspension kind of have the same information, we can use them all the same to measure the diffusion coefficient, which gives us even more statistics. We can look at all these box counts for different box sizes. All of them contain information about what the diffusion coefficient is. And we can use that to get really good statistics and actually measure what these diffusion coefficients are. So here's our table that I hope demonstrates that this is a successful approach. The columns here are different packing fractions. This is the dilute thing we were just looking at. This is kind of an intermediate packing fraction, and this is the very dense one. The first row is diffusion coefficients computed sort of classically using particle tracking and TrackPy and in a modernized version of exactly what I'm saying. The second row is our fit using this Countoscope. Notice the error bars here, we get so many statistics, the error bars are actually dominated by experimental error. So our statistical error is so small that it's dwarfed by pixel size and things like this. So we were pretty happy to see this. We were pretty happy to see that we're essentially getting the same thing as you would with particle tracking, but I would wager, and I'm of course biased, but I would wager that this is much easier than particle tracking and much more robust.
I might have a very naive question.
Yes.
But something is bothering me with the dimensions. On the left-hand side, you have n squared, numbers, particles squared. On the right side, you have numbers. So.
Okay. So.
What am I missing?
We have n squared on the left. So for some reason, I remember this formula working, but the real version, for some reason when I wrote this down using mean n was more natural to me, but what we actually use is variance of n.
Okay, that fixes it. Okay.
Which does fix it. Yeah. I think this was a whoops-a-daisy. What I meant was a scale for the number of particles in the box. And it winds up that they're related, by the way. So this is a little bit technical, but the mean of the number of particles in the box is related by SK0, so structure factor evaluated at wave number 0 to the variance. So they're actually kind of the same quantity. But you're right, the units are kind of weird and I should have used variance there. Good catch.
Dimensional analysis.
Okay. So, by the way, I use mean throughout. So in your mind palace, please replace mean n with variance n. Okay. So another thing that I wanted to point out that I thought was very cool. One of the reviewers of this paper said, "Okay, this works great. Try and break it." So we tried a bunch of things that might break it, things that happen in experiments. Typical problems are maybe your particles blink. You actually lose a particle when they lift, so it's not in your field of view anymore. Maybe your resolution is really bad, and one of the most common problems is drift. So your microscope's on a little bit of a tilt, and there's this systematic drift in the system. You can totally get rid of this with particle tracking methods, but it's kind of annoying. And I was really happy to find that if we just take data and add synthetic drift to it, so we just make it move to the left at some velocity, this is an incredibly robust technique to drift. So I didn't modify anything. This is exactly the same counting procedure as it always was. Compute statistics on the mean square displacement of n and do nothing else. And it just totally ignores drift. And we can show mathematically that the drift velocity, any net drift velocity, would come in a higher order term. So it just winds up not mattering. As long as you're fitting to the lowest order term, you can get away with a fair amount of drift in your system and just not think about it. Okay, so this is all with dilute systems.
Do you going to come back to the plateau later?
Oh, yeah.
Okay.
Hold on.
It's okay. If you're going to say later, I don't ask now.
This many slides.
Okay, perfect. I hope.
Okay, so I would say the plateau is much more interesting for dense suspensions, which is why I've waited for dense suspensions to talk about it. So Before I talk about dense suspensions, just like a quick primer, and I'll probably skip through this really quick. I simulated the system. I simulated the system with an immersed boundary method. The idea is these particles are so small, there's no inertia in the system, so we solve the Stokes equations. I'm saying that these are the force Stokes equations, so let's talk about the forces a little bit. This slide's messy, but there's only a few things to really get from it. The forces on the fluid come from the fact that there's particles in them, so I'm going to treat those forces using a regularized delta function. This is sort of the immersed boundary paradigm. And then we also pick up this div W term. This is W's a white noise tensor. So div W is the divergence of a random stress. This is from Landau and Lifshitz. The idea is that if you want to add randomness into the Stokes equations, you do it at the level of stress because that way it can be isotropic randomness. And then we evolve the position of the particles using the local fluid velocity. We have a nice method to solve those equations, but the problem is that when you use regularized delta functions to account for solid particles, you blur them out. So we call them blobs. So we get these blob-like particles, but really we want spherical particles. We want to be imposing a rigidity condition, a rigidity boundary condition on the surface of the sphere. So we want to treat them like spheres. We want to have accurate near field hydrodynamic interactions. So there's this old trick from John Brady from the 80s about how to do this, how to correct these sort of rough blob-like approximations and make them really act like spheres hydrodynamically. But in the original paper, which I meant to have a citation for, but don't here. In the original paper, it's a wonderful method, but it's computationally really slow. So with Michelle in 2020, we came up with a very fast method to do this so that we could actually correct for spherical particles in suspensions, in big suspensions. Okay. So let's actually talk about dense suspensions now. So I want to show you a video of what it looks like to be in a dense suspension. Now, as opposed to dilute suspensions, you're actually kind of hard-pressed to find a particle that isn't interacting with another one. So now, particles interacting with each other is the norm rather than the exception. So what if we try to naively do the same thing? So the nice thing here about simulations is we can really try every level of approximation. So the first level of approximation in my mind is all the particles are points, they're not in a fluid, they're just diffusing. There's just randomness. So you have point-like particles with no interactions at all. And what you see if you try to measure the mean squared displacement here, particle counts, is that it's way different from if you do this on the actual experimental system. So if I use a box size of 8 microns, this is the actual data. This is what you would get if you did a simulation where no particles are interacting. That's bad. So what happens when you include steric interactions? So now the particles are not in a fluid, but they are interacting. So they can't overlap, but they're not in a fluid. So this is what happens with the plateaus. If all we do is include steric interactions, no hydrodynamics, we get the plateaus right, which means that these plateaus are really telling us something about steric interactions. They're telling us about configurations. They're not telling us anything about hydro. Sort of by process of elimination, because the early time behavior does not agree between experiments and these simulations without hydro. It must be the case that early times are telling us about hydrodynamic interactions. Why is this? It's because when you're in a fluid, you have two spheres that are very close to each other. Their hydrodynamic interactions are severely or significantly modulated by this lubrication layer. So there's fluid kind of trapped in between any two surfaces that makes it harder for these two spheres or these two solid bodies to move relative to each other. So this slows things down and effectively makes the diffusion coefficient bigger because it effectively makes the diffusion coefficient smaller because it makes the drag bigger. So when we add in hydrodynamics, finally all things fall on top of each other. Simulations match up with experiments. And indeed, we capture both the early time behavior controlled by hydrodynamics, and because we also have steric interactions, this plateau. So I want to talk a little bit about what the plateau actually is. So it's a fairly straightforward calculation to show that for long times, the mean squared displacement actually gives you the variance of the number of particles. It's also maybe not that bad to make an argument that the variance normalized by the mean, so the variance normalized by the mean number of particles, tells you something about the compressibility of the system. So these plateaus are really telling us about the compressibility. So you have a simple liquid, a fluid with a bunch of particles in it. How does that change how compressible it is when you apply forces to it? And hydrodynamics are, of course, telling you something about the short time behavior. So hydrodynamics control short time, and sterics control the long time behavior, which physically tells us something about compressibility in these systems. Okay, so this was the part of the story that I got very excited about, because we could actually use this counting technique to make a new measurement. I want to just plot a bunch of these mean squared displacements for a bunch of different box sizes in a slightly denser suspension where something interesting is happening. So this is a 34% packing fraction, and you see that, again, it's kind of the same story. There's this short time, t to the 1/2 behavior, and then you get a plateau. But if you stare at it for long enough, you might notice that there's this kind of characteristic timescale associated with the transition to a plateau. So I can draw, this is like a cartoonish line, just to give you some idea of this transition. But we can also mathematically pick it out. So if we normalize mean squared displacements by the variance, subtract 1 so that these curves are going to 0, we can integrate out a timescale. Once we have a timescale, a length scale gives us a diffusion coefficient. So this timescale is associated with some diffusion coefficient d of L that is now all of a sudden a length scale dependent diffusion coefficient. This is telling us something about diffusion on the scale of a box of size L. And this gives us a notion of what's called collective diffusion. So collective diffusion is something I've learned recently that soft matter people argue about a lot. The physical interpretation of which, this is the one I like, is the idea that in time, if you were looking at that video of the dense suspension of particles, you might notice that every now and then they kind of just get together and hang out for a little while. They would form these little aggregates of particles, and these aggregates of particles you could almost kind of draw a little circle around and then say, okay, that's effectively a bigger particle. So now it moves around like a bigger particle for a little while and then dissolves just as soon as it, well, not just as soon, but, and then dissolves. So there's these transiently formed aggregates that act like bigger particles on length scales that are, say, large enough. There is actually a characteristic length scale that we can associate with the onset of these collective effects, but I won't tell you too much about that. So this is this physical idea of collective diffusion, and the hope is that we can use this notion of this collective diffusion timescale to actually find a diffusion coefficient associated with boxes of size L related to collective effects. So here's a plot of that. So what I did was I took the diffusion coefficient related to a box size L and normalized by the self-diffusion, the diffusion of a single particle in a vacuum. This is what we would get in the, not in a vacuum, but the diffusion of a single particle in a fluid not near any other particles. So for very small box sizes, that's all we measure. For very small box sizes, we might have a particle dip in and out of a very small box, and that'll tell us about the diffusion of just that particle. On the bottom here is the size of a box normalized by the diameter of a particle, and as we get bigger and bigger and bigger here, you see some interesting behavior. You see that this is increasing for a while. The solid curve here is theory. So the solid curve here is what Sophie worked out ought to be happening in the absence of hydrodynamics. So purely from some kind of cool statistical physics argument. With no hydrodynamics, what should be happening as the box size gets bigger and bigger? And it reaches this plateau, which is related to this compressibility. But what we see is when we actually include hydrodynamics, this collective effect is massively enhanced, at least for a little while. And the reason this is so exciting to me is I have genuinely no idea what happens after this point. This is about the limit of what we can get data-wise in simulations or experiments. This represents the best possible data we can get from 48 hours of experiments and like a week of runtime for these simulations. I don't know whether it goes back down. I don't know whether it all of a sudden shoots up and diverges. There's some theoretical reasons you can convince yourself of both, but fundamentally collective diffusion and its enhancement by hydrodynamics is really not well understood. But what we can show here is, at least for a little while, hydrodynamics massively enhances collective effects in the system. And this is a measurement that no one's made before. So we were pretty excited about that. That said, we were excited by the notion of collective dynamics in general. And it's not like no one's ever looked at them before. There's a lot of people that use these things called intermediate scattering functions. There's a lot of spectroscopy that's done to understand collective dynamics. So with Adam Carter, who's a PhD student at Sorbonne, we put out this paper recently, it's on Archive, that does kind of a deep dive into these collective effects. And in particular, compares what we measure with this counting approach to a couple other standard approaches to measure collective dynamics. Okay. So in the last little bit, I want to talk about what we're working on now, which is what happens when there's more than just diffusion in the system. So this is with Grace Mattingly, who's a PhD student at Mines. And she's done a lot of really, really cool calculations to work out actually when you have out of equilibrium systems, what should you look at and what do you get? So the sort of one slide cartoon of this is now, rather than looking at one box at a time, we're going to look at two boxes next to each other. We'll count particles in each box and cross-correlate them. And what this cross-correlation tells us is something about the flux of particles through the shared interface. So that means that there is some background motion, which I tried to sort of render here as like some flashy streaks on the button. So if there is indeed some background motion, then we'll pick that up in the cross-correlation. We'll pick that up as the flux of particles through this interface. So Grace and Sophie worked out that this is now the right short-time relationship. Notice now it's linear to t, which is kind of interesting, but also it's really simple, which I like. There is some scale for the variance of the number of particles in the box. V here, which is what you're looking for. This is the background velocity. Only in this direction right now, but this is the background velocity. And then the length, some notion of the length of these boxes. So you can do the same thing, compute the cross correlation, and then you can back out, given some knowledge about characteristic means or variances, a number of particles in there, you can back out what the velocity, the background velocity is. So I'll just show you this system that we've been looking at a while. This is data from Alice's lab on a nanopore system. I think looks really neat. This is pressure driven, so there's a pressure gradient here and here. This pressure drop tries to force all of the particles through this very, very narrow gap. So these are about 2 micron particles, so this gap is around 10 microns. And what's so interesting about this system to me is if you look at it, the particles are moving very, very slowly here, very, very fast through the pore. So there's like a lot of heterogeneity in the system. So it's a cool example to look at because this is one of the advantages of counting, that we can really think about heterogeneity. That said, we also want a system where we have a ground truth so we can see how good we're doing. They got so much data for this nanopore and spent hours and hours and hours in TrackPi that they were able to actually track it. This, by the way, is, I don't know, like 10% of the tracks. It's just impossible to look at if I'm showing all of them. But we have a lot of data. We have a lot of data to get at something like a ground truth in this system. So I want to talk a little bit about the counting approach, and then I'll pretty much be done here. The picture that I just gave you was, how do we pick up a background velocity if it's only going one direction? But now, we only have particles coming up and through here. So we also want to pick up on background velocities in another direction. So all we do is rotate the boxes, count vertically, count horizontally. This gives us two basis vectors for our velocity, and in kind of a classic CFD style, we could say that the net velocity at this point is the vector sum of those two things. So now, rather than boxes being our fundamental observation domains, we have these sort of cross shapes, and we can place a cross shape wherever we want in this domain and pick up on a velocity there. So PTV is particle tracking velocimetry, which is, all right, you have all of these tracks. Now you can, once you know where a particle is at any given time, you can calculate the velocity and bin it to get a velocity amount. PNV is what we're calling particle number velocimetry, and this is what we get, which I would wager is very, very similar. We're very, very happy to see this. So this is still very nascent. We're working out a lot of details, in particular, how well does it work for dense suspensions? How well does it work when you use different box sizes? Can you get different information out of using different box sizes? Can you fit better? So there's a lot of open questions here, but preliminarily, we were really, really excited about this technique's ability to actually pick up background velocities in these systems. In particular, there's one method I didn't tell you about called particle image velocimetry. Has anyone heard of that? This is a standard technique in fluid dynamics. You inject little particles into the fluid system and basically track them. No, you don't basically track them. You look at, sorry, I don't know why I said that. I was thinking about something else. No, you very much don't track them. It is, you take the images, and you do an image analysis sort of thing where you look at a little group of pixels and then you imagine if that group of pixels had moved in some direction and you correlate it in each direction. Good. Particle image velocimetry we have compared to in these systems totally could be a skill issue, but when I use some kind of out-of-the-box software to do this, it just totally couldn't do it at all. So I thought this was cool, that there's this method that everyone thinks is like the gold standard that for microscopic systems really falls apart, and our new shiny method really goes pretty well in this case. So, I think that's all I wanted to say. Yes, this is my question slide. So I had a few more slides after questions on simulations or some theoretical stuff on stochastic density functional theory, but I figured I'd then see if anyone has any questions and all that.
Yes. And again, about the plateau, you see it in the like 2% densities and stuff. But you say that are you just capturing those very statistically unlikely transient, like collective fluctuations?
The plateau and the collective dynamics are different.
Okay.
I would say
like what is the plateau in the really low density system?
The plateau in the low density systems just corresponds to the fact that there is.
Is it just the statistics issue?
It is just that an ergodic system, and there's a finite number of particles in it. So the plateau tells you something about the fact that there are steric interactions. Eventually, the particles will feel each other, and so there has to be steric interactions in it. So eventually, you'll see a plateau. The plateau is lower for denser systems and higher for dilute systems, and even at 2%, you'll pick it up no matter what, because eventually something. What the signature of the collective dynamics is here in this dilute suspension, everything rescales perfectly. So no matter what box size I'm looking at, they're really on top of each other. This, by the way, actually isn't quite true. You can still pick up on collective dynamics even in this 2% system, but it's very nasty. Okay. This is basically what this whole other paper is about. Like, are there collective dynamics in relatively dilute systems? But it's about the visual signature of it is the rescaling. For the really dense systems, these things don't rescale at all. They look like so there's like a lot of stuff happening in between. It's very different from box size to box size. So that's where you see the collective dynamics. And the variance, the plateau is really just telling you about the variance, which is really just a property about scales. Yeah.
I have a question about the comparison to PIV. So
yes.
you said that Is the issue here that it's the small scale dynamics, so there's more stochasticity?
I wish I could tell you more about why it doesn't work. I am no expert in PIV. I can just report that I tried PIV. I shouldn't name a software in case. I tried a software, followed the instructions, and it didn't work at all. Like, I mean, really, not just like a different looking velocity field, but like order of magnitude different scale. Now, I agree, but my understanding from the literal Wikipedia page, again, I'm not an expert in PIV, the Wikipedia page seems to imply that PIV really breaks down for moderate Peckley numbers, where the background velocity and the diffusion are really kind
Also,
of
PIV
similar.
requires a lot of secret sauce to make it work. Like everyone talks about it as if it's some gold standard, but there's a lot of secret sauce that you have to.
This is very good to hear. Okay. So yeah, I kind of got that impression.
To be fair, if your PDV work, PIV should work, but you have to play.
But you have to mess with that. This is what I figured. So it likely was a skill issue, but I can report that like I, as an outside observer, was not able to get it to work in an accurate, which is something, I think.
So there was a book written in probably the 90s by some Germans really looking carefully at how you do PIV.
Oh,
Kind of what the fluctuations should be, how far the particles should move. And I think it helps, and people don't really pay much attention to it. I think it kind of fell away when PTV came into vogue, and it kind of forgot about it. But there is a reference out there.
Oh, okay. Good.
My question is, your dilute systems, as Einstein noted, aren't really dilute. You're tracking big particles.
Yeah.
So it makes me wonder, in your dense systems, where you have lots of these big macro 10 micron, 1 micron particles, if you artificially color those like you showed in your first slide, just call some of them blue, some of them purple. Can you look at those subsets of particles and recover dilute statistics? Or is it really the correlation that's induced by the high packing fraction that's causing the differences in the plateaus and lack of scaling?
I would wager, we've done something like this, and yeah, you always feel the signature of the density. So if you just pick a couple of particles out in this dense suspension, you'll get kind of rougher statistics. It's harder to do things because you're throwing things away. But you will get out that diffusion, the sort of density modulated diffusion of the system all the same. So yes, it absolutely feels the fact that hydrodynamic interactions are being modulated by other particles nearby, which is, I think, very cool.
Yeah.
That said, another interesting idea with that is, what if you have binary systems and you call one big particle and one little particle and see what happens there? I have no idea. This is something we really want to try, but there's a lot in this idea of sub-labeling and counting that you can do and provide. A lot of this is sort of theory limited, like, okay, we can do it, but what do we get? Which makes it a fun applied math problem because
we work on granular materials, and we're looking at diffusion problems in those right now in binary systems where you can vary the continuous and dispersed phases between them by changing the fractions. So if we see anything interesting, we'll be in touch.
That would be very cool. Yeah. Excellent.
Can you go to the diffusion plot with different packing fraction? When you plateau, I just want to see the time scale for that. Because at different packing like this, the time changes, right? When you draw that, I'm just curious.
Box sizes, but
different box size. So because I think at the beginning you mentioned with different packing fractions, no?
Oh, so I have a table with different packing fractions.
Yeah.
Yes. Way back here. Yes.
Like even previously, just when does that comes in? Because I'm curious, if you mentioned that it's sterile attraction, then the lower packing fraction one should happen in the later time scale. You should see that. And there should be a scaling law for that time scale to happen.
The lower, sorry.
Like with less particles, you should see the plateau later. Right. You need more statistical models to see that.
Yes, actually something really weird happens.
Okay.
For the very, very high packing fractions, all of a sudden it goes back down.
It goes back down again.
I don't have an understanding.
That's why I want to see. Okay.
But my only understanding is seemingly like near crystal transitions. Weird.
We were stuff.
I don't know. Yeah.
Okay. I see.
There's one question.
Oh, yes. Hold on. Angie, hi.
Hi, Brennan.
Would any theory change if we use circles to count instead of boxes? Yeah. Okay, so I can answer your second question. Your first question is very interesting. The second question is just, we use squares because like microscope frames are usually squares. So squares pack good in squares. That's it. But do you get anything interesting out of circles? I bet you super would. And there are reasons to, especially given that we seem to be able to overlap. Again, I'm not like staking my flag in that, but we seem to be able to overlap observation boxes. Then circles probably tell you something much more interesting because circles are isotropic and they would not have whatever weird corner effects might come from boxes. Although, I mean, admittedly, we don't see any corner effects from boxes, but I wouldn't be surprised if there's something in there. So using circles is a really interesting idea. I will call later and we can talk about that. So hello in Philly. Yes.
Do you get anything specific from having a grid of tiles, or would you like, as opposed to maybe like selecting random locations?
Oh, yeah, okay. So the reason we use grids often enough is literally because it's easy to program. But no, there's a version of the code where, yeah, and this is actually the overlap box version, where you just give it a point cloud. So you have some observation box and you just give it a point cloud of centers and the lengths can be different, and there can be absolutely no order here. And the advantage to it, we're only just starting to look at heterogeneous systems. And the advantage here is a system that is particularly interesting is I've told you that like dense systems are weird. The dilute systems are easy, but what if you have both in one system? So there's like a gradient of particle concentration. Now all of a sudden, yeah, you want to maybe use a lot of small boxes here and a couple of big boxes over there. And in principle, as long as you kind of dot your I's and cross your T's, there's no penalty for doing this. You lose statistics because we really benefit from if you use the same box everywhere, you get a lot of statistics. Whereas if you're only looking at a time series for one box, you need a long time series. But yeah, this is absolutely something you can do, especially with good data. So we're starting to look at these things. Yeah.
So I think because the particles are in the fluid and that brings an interaction, you get these aggregates. Mm-hmm. And so I wonder to what extent that you look at the structure of these aggregates, because what I would imagine is that the fraction of space that is occupied, that distribution would change. And so you then could be talking potentially about an effective number of particles that is different from the real one, and it also has a distribution of sizes.
Yes.
And to what extent that could be used to explain some of the deviations and account for our higher order effects.
This is a very interesting idea. I think it is actually, and we're only kind of starting to unpack that. And I think you're right. And some of that information really is contained in this D of L, the idea that you can look at a diffusion associated with a box size. And in this other paper with Adam, the one that's on archive, we looked at this carefully and we compared to intermediate scattering functions, which are related, I think, to this idea. At a minimum, you can now ascribe a length scale, or at least a length scale in Fourier space, to what you're seeing, which I think, I would say I have not seen any really convincing physics that this can be directly related to the size of a particle aggregate, but I think you probably can in some way.
I think it would be at least very interesting to characterize it, right? Because
yeah, absolutely.
Sort of figuring out how long do they last. I mean, it sort of becomes more important as the density is very high, but even in the low ones, in the videos, I noticed some pairs of particles that came together, stayed together for a while, right? So there are these periods, and probably there is a relatively constant fraction of such periods that exist at a time. You could simplify some calculations.
I completely agree. I think it would be very interesting. And there's even some natural things you could say. Like in dilute suspensions, you wouldn't expect more than 2 or 3 at a time. In dense suspensions, maybe there's different scales. You would expect 2 or 3 and 5 or 6 and 12, like you could probably start fitting. This is about, yeah, I'd be interested to talk a little bit more about this, because I think there are actually some things that we can say at least low level just from DML.
And you're out of time.
So thank you all so much for coming. I'm actually around all week, so if anyone wants to talk about anything, I'll love talking about this stuff. So, thanks.